So today we're going to continue our discussion of vapor-liquid equilibrium, particularly focusing on mixtures. Mostly going to deal with binary mixtures again, but the concepts that we talk about will apply to mixtures containing many components. But we're going to look at the how we can use mathematical expressions to analyze vapor-liquid equilibrium. So we had previous videos where we had graphical methods, and now we're going to look at a more mathematically oriented method. So one of the things that we need to talk about is the K value. So the K value is just defined as such that the K value for a particular compound, and this I've just labeled I could be species A, B, C, or whatever. It's just the ratio of the mole fraction in the vapor or gas phase to the mole fraction in the liquid phase. So the great thing about the K value is once we know what it is, if we know what the mole fraction of a particular compound is in liquid, we can find what it is in the vapor or gas, and vice versa. If we know it in the gas, we can find it in the liquid. So knowing the K value is really important towards understanding and describing vapor-liquid equilibrium. That's the equilibrium again between the gas and a liquid. This K value, it's a very complex function many times. It can be a function of the temperature, it can be a function of the pressure, it can be a function of also what else is in our mixture. So if I have a mixture of ethanol with water, the K values may be different than, say, a mixture of ethanol and methanol. So it can depend on all of these different things. And so we just have to be aware of that it's this function that sometimes can be complex, sometimes can be simple, just depending on how we go about on the type of mixture or system we have. So let's just talk about Dalton's law. So you might have seen this sometime in your chemistry courses before, but you've probably forgotten it. But Dalton's law just relates a gas mixture, and if it's a multi-component gas mixture, it relates how those different components relate to each other as far as the pressure of the system. So here's this mathematical formulation of Dalton's law, which just simply says that the total pressure in this gas mixture is equal to the sum of the pressure of each individual chemical. So I have A and B and C and D and so forth. It has more than two components. But the pressure of each individual component adds up to the total pressure. So if this is a 50-50 mixture, we may have, and the total pressure is 1 atmosphere, then 0.5 atmospheres may come from species A, and then 0.5 atmospheres may come from species B. So there we have this equation here that relates the total pressure to the individual pressures that contribute to that total pressure. Well, the repercussion is that the mole fraction in the gas state is equal to the pressure of each individual component or each individual chemical divided by the total pressure. So this is a lot like our mole fractions for moles. In this case, instead of having mole species I here divided by the total number of moles, it's just the pressure of species I divided by the total pressure here. And so we sometimes might use Dalton's law when we're analyzing vapor state or gas state of mixtures, especially when we're dealing with vapor-liquid equilibrium. So before we start diving into looking at K in detail, these K values, we need to go over a few other things. So the first thing I want to go over is Raoult's law. So Raoult's law is often used in analyzing mixtures, and it specifically applies to ideal solutions. It's the ideal case for a particular mixture of two or more compounds. And Raoult's law simply relates the pressure of particular species. In this case, I'm just doing A, so we might have a mixture of A, B, C, etc. So if I measure the pressure of species A in the gas phase, so again, I'm measuring the pressure in the gas phase for a particular species A. That's the amount of pressure that it gives to the total pressure here. That's equal to the mole fraction of species A in the gas phase multiplied by the total pressure. And that's just the definition of pressure of species A. It's just the fraction of the total pressure based on its the mole fraction. And that's equal to the mole fraction of A in the liquid, down here the liquid, multiplied by this PA star. And what is PA star? PA star is just defined as the vapor pressure of the pure liquid. So in this case, we could calculate PA star just assuming that the particular A is in a pure liquid state and it's at the particular temperature of whatever this mixture is. And so we can calculate this, for instance, from Antoine's equation. So we might use Antoine's equation to calculate PA star. This is the whole Raoult's law right here. And this is the real utility of it, is it allows us to relate Y and XA based on the pressures. So here's the total pressure above the system of the whole entire mixture, and here's the pressure of the pure liquid in the vapor, or its vapor pressure of the pure liquid. So we can relate the compositions or the mole fractions of A and B, or A in the liquid and vapor state. And we can also write out similar equations for B. I could write out a different equation, but just replace this A with B everywhere. But that's the Raoult's law. So very related to Raoult's law is Henry's law. And so Henry's law is kind of a variant of Raoult's law. It says that the pressure of a particular species, in this case it's A, chemical A, is equal to the mole fraction in the vapor or gas state multiplied by the total pressure, and that's equal to the mole fraction in the liquid state multiplied by this HA, and this HA is Henry's law constant. And it, depending on the compound, every different chemical or compound will have a different Henry's law constant. So it's similar to Raoult's law, but rather than having this, the vapor pressure, we have Henry's law constant. And let me just say that Henry's law tends to be more valid in the case where XA is very low, close to 0. On the other hand, Raoult's law tends to be more correct when XA is close to 1. And Raoult's law may be valid over a larger range of XA values or mole fraction liquid, but it tends to be more valid when it's close to 1. So Raoult's law and again Henry's law, both approximations to describe the equilibrium between a liquid and a vapor state. And again, it relates YA to XA as shown here. So gone through these different sets of equations. We had Dalton's law, Raoult's law, Henry's law. Well, let's put it all together. So if we have a binary system, that means two components, we can combine these different equations together to come up with solutions for the vapor-liquid equilibrium for a mixture of these two components. So here is our combined Dalton's law, Raoult's law, put it all together, coming up with the solutions to what we want. So we have YA, that's the mole fraction of species A in the gas or vapor phase, is equal to the vapor pressure of pure A at that given temperature times the mole fraction of A in the liquid phase divided by total pressure. The Ka that follows from this is simply the ratio of YA to XA, and that's equal to the vapor pressure of A, pure A, divided by total pressure of the mixture. For a binary mixture, that means just only has two components, maybe components A and B. If we combine the mole fraction equations and so forth and do a little math and algebra, we come up with these two equations right here that relate YA and XA based off of vapor pressure of the pure substances and the total pressure. So the take-home message from this is, if we are using Raoult's law and it applies, and we go through all these simplifications that I've shown you, all we need to find out the mole fractions in the liquid or the vapor phase is the vapor pressure of the pure substances, which we can find from Antoine's equation, and the total pressure here. So if we find XA using these pressures here, we can plug it back into here and find YA. So it's very nice and convenient that we can make these simplified approaches to calculating vapor-liquid equilibrium. Again, it relies on Antoine's equation, that it's a correct Antoine's equation, the parameters are valid. It also relies on whether Raoult's law is valid or not. And sometimes Raoult's law doesn't apply, but if it is, then these are the type of equations we'll use. Let me just add on a few more things to this. One is, how do we deal with non-ideal solutions? So Raoult's law applies to ideal solutions. What do we do about non-ideal solutions? So here's the equation that we use for non-ideal solutions. The only difference between this and an ideal solution of Raoult's law is this part right here. And this part right here, this term is what we, correction term, to correct for the non-idealities, it's known as the activity coefficient. For an ideal system, this activity coefficient is 1. And if it's 1, then this equation just simplifies to the case for Raoult's law. For a non-ideal case where Raoult's law may not directly apply, we have to add in this correction term, again, the activity coefficient. So this is one way that we can get around to modeling or describing non-ideal solutions by using a Raoult's law type equation, but go ahead and plugging in this activity coefficient right here. Right there, the activity coefficient. So the next concept, relative volatility. So relative volatility, this term here, this alpha AB, is just simply the ratio of the K values of two particular chemicals or species. In this case, it's the K value of A divided by the K value of B. And the relative volatility tells us how volatile they are compared to each other. So a larger relative volatility value here would tend to mean that species A tends to be more volatile than species B. So it's just a way to compare the volatility of two components. So let's just look at the case of a binary mixture. So again, this is a mixture where we have only two components, A and B, and we're assuming that Raoult's law applies. So if that's the case, then the relative volatility just simplifies to this expression. So we take some of those equations that we developed from Raoult's law and so forth and plug them in to this up here for the Ka and Kb values, and we get this, where again Pa star and Pb star are the vapor pressure of the pure liquids at the particular temperature we're looking at. And so if we do some mathematics, simplification, some algebra, etc., we'll get this equation for the relationship between Ya and Xa. So this is just a simple equation that if we wanted to, we could take this equation and we could plot it, Ya versus Xa here, and we can make a Yx plot. So we've seen those Yx plots, and this is a way to do that if we know the relative volatility. It also assumes that the relative volatility is constant across the entire spectrum of mole fractions, and also at different temperatures, but if it is, then this is the particular equation that holds. And so relative volatility is, again, another concept that we can use to quantify the vapor-liquid equilibrium, and also if in certain cases under binary systems that are ideal, we can use it to plot XY data, like shown here using this equation. So let's just put this all together. Got all these equations. What are we going to do with it? Well, ultimately, one thing we're concerned about is making XY and TXY plots, because those are what we'll use to analyze the vapor-liquid equilibrium and help us design different separations processes. So we've gone through all these different equations. Well, here's a kind of a breakdown of how we apply all these different equations. Well, first thing, we wanted to know if Raoult's law applies, because a lot of these equations I've shown you here in this video are valid for Raoult's law. So we need to know if Raoult's law is valid. Assuming it's valid, then what we do is we fix the total pressure. Once we fix the total pressure, maybe 1 atmosphere, that's a typical pressure that we work under, we choose a temperature. So we choose a temperature, and from that temperature we are able to calculate the vapor pressures of the pure substances using, for instance, Antoine's equation. And then once we know the vapor pressure of the pure substances, we can use the various other equations to calculate Xa and then calculate Ya. And then we choose another temperature, calculate the new vapor pressure, Xa, Ya, choose a new temperature, and then go down the line here. And we just keep iterating here, choosing new temperatures to get different vapor pressures, Xas and Yas. And when we've done that, and in the end we'll get a list of different temperatures, the Xas and the Yas at those temperatures, and then we're able to put that all together to make our TXY plot or make our XY plot. And that's pretty much the method here of how we go about doing it, applying these equations. We just have to have a way in order to calculate Xa and Ya as a function of the temperature and also of the pressure, and the equations that we've developed allow us to do that.